Have you ever stopped to think about a camera flash? I mean, how does it create that incredibly bright burst of light in literally a split second? Or think about a defibrillator delivering a massive jolt of electricity to save a life. The secret behind both is a tiny, brilliant little component that's an absolute master at storing and then dumping energy in a flash.
And that component is the capacitor. Today, we are going to pull back the curtain on these pocket-sized powerhouses and figure out exactly what makes them tick. So, let's dive in. All right, here's the plan. We'll start with the basic idea of capacitance itself, then we'll look at a wild, planet-sized example to put it in perspective. After that, we'll see how we actually engineer these things, and finally, check out some of the other shapes they come in. Okay, first things first. Before we can talk about capacitors, we have to understand the core concept behind them, this idea of a capacity for charge. So basically, any object that can conduct electricity has this property called capacitance. It's really just a measure of how much electric charge, which we call Q, an object can hold on to for a given amount of electrical pressure, or voltage, which we call V. The formula tells the whole story. Capacitance, C, is just the charge, Q, divided by the voltage, V. Now, the unit we use for this is called the Farad. And to really get what that means, think of it like this. Imagine voltage is the pressure you're using to fill a bucket with water. Well, the capacitance is just the size of that bucket. A bigger bucket, a higher capacitance, means you can hold way more water, or in our case, charge for the exact same amount of pressure. Okay, to make this a little less abstract, let's scale things up, way up. Let's think about the capacitance of the biggest conductor we all know, planet Earth. Now, for a simple conductor, like a perfect metal sphere, figuring out its capacitance is actually pretty straightforward. It really just comes down to its physical size, specifically its radius. The bigger the sphere, the bigger its bucket for holding charge at a certain voltage. So what if we treat the entire Earth as one giant spherical conductor? What's its capacitance? Well, it's about 711 microfarads. That's tiny. That's not even 1/1000th of a single farad. For a whole planet, that is shockingly small. And this is the key takeaway. We can't just rely on random objects to store charge for us. We need to design things specifically for that job. And that brings us to the hero of our story, the capacitor, a device that is specifically engineered to cram as much capacitance as possible into a really small space. The most classic textbook design is the parallel plate capacitor. And the idea is just beautiful in its simplicity. You just take two conductive plates and you stick them really, really close to each other. But, and this is critical, you don't let them touch. Now, when you hook these plates up to something like a battery, something cool happens. The battery starts pulling electrons off one plate, leaving it with a positive charge, and it pumps those same electrons onto the other plate, giving it an equal and opposite negative charge. This separation of charge, this tension, it creates this neat, uniform electric field in the gap between the plates. You can see it represented by the arrows here. And that field is where the magic is. It's not really the metal plates that store the energy, it's this electric field that holds it, all coiled up and ready to be unleashed. So if you want to build a better capacitor, one that can store more charge, well, the physics gives us two simple levers to pull. First, make the area of the plates, A, as big as you can. And second, get those plates as close together as possible, shrinking that distance, D, without them touching. It's that simple. More area, less distance, more capacitance. But you know, capacitors don't always look like two flat plates. The same exact principle works for all sorts of other shapes. For example, check these out. On the left, that's a spherical capacitor. It's basically one metal ball inside another bigger one. And on the right, you've got a cylindrical capacitor, which is just one tube nestled inside another. The shapes are totally different, but what they do is exactly the same. Because at the end of the day, the fundamental principle never, ever changes. It doesn't matter if it's flat, round, or shaped like a tube, a capacitor is always just two conductors separated by an insulator. That's the secret sauce. So there you have it. From the tiny circuits in your phone to the massive power grids that light up our world, capacitors are everywhere. They are the true unsung heroes of electronics, silently mastering that art of grabbing energy and then letting it go in an instant. And that kind of leaves us with one last big question to think about. We know capacitors are masters of instant energy. So as we push into the future with things like electric vehicles or even fusion power, where else could this incredible fundamental principle completely change our world?